So this is what we ended up with as a way to abstract and make things a little bit simpler. And it's not quite as elegant as I would like, but it is getting there. So let's go through it a little bit carefully here. Let me maybe expand this so it might be easy to see.
Yeah.
Can you see that?
Yes, yes.
Okay. So one way to view gamma or upsilon, upsilon is a type constructor. So it takes types tau to this disjunction, this tagged disjunction. So you either have an R of tau or circle n of tau or a row tensor of tau and tau, etc. So that's one way of thinking about this. It's of course underneath it's a functor, right? If you're gonna model it in category theory, then you have some. Then you can think about each level of the types as some prefix that's some generators, and then upsilon. So right, so it's the closure, right? The recursive closure. So here the generators are whatever constants you've got plus the identities plus the K, right, which is the interactive structure, and then upsilon. And then the collections are going to be roughly the same, right? So your generators for collections are going to be top, bottom one, unit of tau, which is given up here, product. And the reason we've left K out and of upsilon up here is because we want to restrict it here and here. We may put it back in if we give a good map interpretation of K, but for the time being, we want to restrict it. We don't want to have it automatically included here, which is why we're repeating it here. But hopefully that makes sense, right? So you've got some prefix of generators and then your upsilon. So does that correspond with what you were doing?
Oh yeah, exactly.
Yeah, so you can write this in Haskell or Scala, but you can't. This, in other words, it works as a data definition language, but from the point of view of a grammar, this is actually sort of bending the rules. This is not really a grammar. It's a data definition language.
Now it's much more clear.
Yeah, exactly. But what that means, therefore, is that we we'll have to go back through. So here, these are all, the container manipulation is all in terms of taus, and that needs to be changed to sigmas. And similarly, for the context manipulation. Right, so for the arrows and the lollipops, we're going to have exactly the same issue where we have to change these from taus to the corresponding arrow types, either arrow or context.
I have just one comment.
Yeah.
You're using tau for as the variable and also for definition of the structure. So
Oh yeah, but that's on purpose so that so they can line up. So when your eyes see them, you see that they line up.
oh, I see.
Yeah. All right. Well, that's really the sort of the main improvement here for this week. Any questions? Do folks understand, sort of what's happening here? Sounds like Tomislav, you do, but
Yeah, I think that I now have a good understanding.
yeah. So the one of the important things is the distinction between these kinds of contexts and these kinds of contexts. Maybe we should change from arrow and context to something like linear arrow or linear context and context. I'm not sure quite what, or intuitionistic context and linear context. I'm not sure. So these things here, essentially the types are recapitulating the term structure. And you can see how this decomposes nicely. So if you go up here, this is the theory we're given, right? So there's the generators and then the rewrite rules. And then we add the resource theory, which gives us all these constructors, right? So that resource theory is essentially this thing here, right? So you're given some theory and you add resources to it. And then similarly, you're given some theory. So there's the tau. You're given some theory and you add a notion of collection to it. And similarly, you add a notion of intuitionistic context, and you add a notion of linear context, right? So now the type system reflects this idea of starting from some kernel and how we're adding, how all the pieces get added together. So that's the important thing is what's the kernel, and then how are the pieces added, and then the inference rules have to then reflect that. But this is being able to show this decomposition in terms of what's core or central and then what's derived is very important, because the whole idea is that this is algorithmic, that this is generated as opposed to done by hand. Right. So that's really critical to the whole program, is that this is not this is not some delicate by hand construction. It's there's an algorithm here. Does that make sense?
Yes.
Cool. Does this make sense to anyone else besides Tomislav?
Well, sort of on a very, very high level, that something is derived from something else, and this is cool.
Well, let me see if I can make it make sense. So here, one way to think about this. So you're familiar with rho at this point. So think of K as par. So tau is going to be the type of processes, and this is par. And these things are going to be whatever built-in constants you have. So, so in the case of rho, right? Since we have it, we've said every concrete data type is a process. So that means that you know, all the strings, all the Boolean constants, all of the constants would come in here. All right, so that's par. That's all the constant data structures, the data values. And then these two things, it turns out that, you know, if we're trying to be abstract, you may or may not have either a left identity or a right identity, but you have to have at least one. So in the case of lambda, as opposed to rho, you have a left identity. So you have an LK. In the case of rho, you have par is commutative, right? So you can swap these around, which means that the left identity and the right identity coincide. They're one and the same, and that's 0. So does that make sense?
I think so.
Okay, so this is an what we're saying is whatever theory of computation you give us, it has to have at least this much structure. So the K part is saying you've got to tell us how when you put two terms together they evolve. So in the case of rho, when you par two terms together, if they are input and output and they match certain conditions, i.e. the COM rule, then they're going to evolve. But all of that happens because you formed a par, right? In the case of lambda, you make a step forward if you've applied a term to a term. So K is application in the case of lambda. And we're saying we don't really care what the constructor here is. It's just that the constructor has to have the shape of taking two terms. And one way to think about that is that it's program and environment. So in the case of lambda, the program is the lambda abstraction, the function, and the environment are the values that we're applying the function to, the arguments that we're applying the function to. In the case of rho, you could think of it as the for comprehension and the output. But again, because it's commutative, you could just as easily dually think of it as the output and the for comprehension, right? So the idea of program and environment is still present, but you have a duality between the two in a certain way. But we're insisting that whatever your theory of computation is, whatever your model for how computation proceeds, whether it's the Java VM or JavaScript or the row calculus or the pi calculus or the lambda calculus, you have to have some constructor that takes two programs and combines them, and that combined program is the thing that will evolve. Does that make sense? Yeah,
it makes.
Okay, cool. Go ahead.
In the end, you mentioned that we have two programs, and in case of lambda, it's a function and the data. So it's a program.
It's basically calling a function.
Why is it a program? A lambda abstraction is a program. A piece of data is a program. In lambda, everything is a program, right?
Okay.
And in rho, everything is a program. There's not a single thing that isn't a program.
I see. Okay.
Okay. So what we're saying is, no matter what your theory of computation, it has to have at least this much structure. And if it has this much structure, then we can automatically take enrich or enhance that structure. And this is pretty much the way we've enriched or enhanced the row calculus with cost accounting. Okay, so what we say is, we're not going to let you evolve without a special token, some resource, R. So before, you could just evolve because the two programs had a certain shape. So in the case of Lambda, the shape was abstraction and data, right? As long as it was K of an abstraction here and some data here, this could take a step using beta reduction, right? Function application. You substitute the value in for the parameters of the function. Or in the case of the COM rule, it's very similar, right? First you wait to have the value communicated over, and then you take that step. And what we're saying is, no, we're not. We're going to suspend that operation. You don't get to do that operation unless you have one of these tokens. So the first construction for this new resourced theory is that R, you can, given some program, you can apply R to it. So you can think of R as like a function or a data constructor that takes a program and wraps it up in an R. And so if you have an R of a K, then it can evolve. But you could take R's of other things as well. And you have to talk about how whether or not the R can float upward outside, from something inside here to out here, so that this can evolve. And so there's some equations around how these resources behave that have to be specified, and they're specified up here. But in terms of just the basic structure, R is like a type constructor. You can wrap programs up in R's. And as a result of that, if you deny a K a resource, then it's like a computation that's been frozen. It's stuck. It can't go farther because there's no rev available. Does that make sense?
Mm-hmm.
Okay. Since it's stuck, you could think of this as like now it's it's another kind of data type which represents computation that's suspended. And so one would like a way to extract the components of the suspended computation, right? So if I make a computation that's ready to go but can't go because it doesn't have any resource or rev, then you could imagine that if I wanted to write a debugger, the debugger wants to be able to look inside the suspended computation at the components that are suspended, right? So look inside the application and see the function or see the arguments. Is that making sense?
Mm-hmm.
Okay,
Yes.
good. So then there are two, if we imagine that we're going to we're going to have a discipline on how we can extract those components. The only way we can extract them is using the method of computation that has been provided, right? So we don't get to like go build accessors like in Java or Scala or something like that, because that's a very specific model of computation, right? So we can only use what's been given to us, and what's been given to us is the C through K. So if you wanted to inspect something that's the two components that are frozen inside K, well, what you're forced to do is to wire them up to other things that some probes that you've built, some programming probes, and then wire them all up in a K. So let's say you have a probe 1 and a probe 2. Those are just going to be towels. They're just going to be programs. And now you can wire them up inside a K. So you have K of probe 1 and probe 2. And now there are two ways that you could have those probes investigate what's inside here. So if I have K of probe 1 and probe 2, I could have the probe 1 wired up to the first component and the probe 2 wired up to the second component. In other words, I can wire them up in parallel.
I'm not sure I follow here. So,
okay,
so tau is a programs that, so we are executed these K of tau and tau, and during the execution it's stuck because it doesn't have the resource to continue.
Yeah.
And now we are talking about this tau and tau as the probes, but these are programs that are stuck.
Yes, that's exactly right. So I'm gonna expand out the the screen share here for a second, so I can draw for you. So this is the kind of engagement that's really important. Okay, so we do screen share. So we have K, and now over there, tau was a type variable. So when I'm actually forming a real program, I've got to have an actual term. So I've got a term, say T1, and I've got a term T2. And let me make this bigger. Okay, hopefully that's big enough. All right, so these two, so that's a term, and then K of those two things is also a term. And now I'd like to be able to get some information about these two things. So think about it like particle physics. In physics, I don't get to just write an accessor on an atom and have it give me all its neutrons or protons or electrons. I have to actually work within the laws of physics to do that. So one way that I work within the laws of physics is I collide another atom with this atom. Well, so there's an atom. So what does another atom look like? Well, another atom is going to look like K. And now because these are probes, so the one thing I can do is I can design the kind of atom I'm going to smash against this atom. So, here's, this is bugging me. Let me fix that. Okay. So I've made an atom out of a particular kind of internal structure that I designed. And because I designed it, I know that when these parts interact with these parts, if certain events happen as a part of the evolution, then I've gotten good information. I've got the information I want, right? So that's what's available in, let's see, bring up the Brave browser. That's what's available to us here, right? The only thing we've got is the theory of computation. The only thing we've got are the laws of physics, right? So I don't get to go outside of that. So now given K, there are two ways that I could wire this up, right? Because K is going to tell me how I can create collisions, I can create interactions. So there's only two ways, and one way is I make a K. Let me just. I make a K out of this one. Oh, sorry, whoops. And I make a K out of this one. So you can think about it this way. I can form two kinds of collisions. I can collide these two things this way so that I end up with a K on the outside.
I see. So basically, here tau is the K of T1 P1.
That's correct.
Okay.
Well, I mean, to be really accurate, there is a tau, which is the K of T1 T2. There is a tau, which is the K of P1 P2, and et cetera. Yeah, but I think you got the idea. So this way of taking this piece and this piece and this piece and this piece and then putting a K over all of that, that's literally wiring a circuit up in parallel. Does that make sense? So if you think about this as a circuit and this is a circuit, I've run the wires in parallel. Right. And so there's also the other way I could run it if I think about them as circuits, right? I could run it in series. So I could do this one. So I leave these two alone. So I let them go ahead and run against each other. And I let these two run against each other. And then I run the result of this against the result of this. And that's running the wires in series. So if we go back to our type constructors, this is basically the denial. This is making a K without an R. So that's our tensor constructor. And this is extracting the components in parallel. This is making a K without an R. So it's literally the same as that one, but in this new idea that I've that the only way I can extract the information is in series, and this is extracting the information in series. Extracting in parallel, extracting in series. So that's the whole idea, is that you give me some laws of physics, and now I'm going to adjust the laws of physics so that it costs energy to run the laws. And then that gives me these new constructors about how I can smash particles together to learn information about those particles. And then this last one here is set. It says, it basically tells you how much R is present. You have NR, which is going to let you get down to tau. So if after n steps you get down to tau, then, so if the program satisfies this type, that means there's NR and it can make n steps to get down to tau. Now, it's a little bit tricky because in the case of par, you could have n terms that are all parred together, each of which are wrapped in R. So it's not really n steps in the sense of n sequential steps. It's potentially n parallel steps, but it could also be n sequential steps. Right. So you could have an R on the outside of a COM, but on the inside of the continuation of the for comprehension, there's an R inside that, and so on and so forth n times, right? And that would give you the another legal program that satisfies this type. Does that make sense? Or should I draw it out? Let me draw it out.
Sort of, but I got a bit blurry when you said about these wiring circuits and talking about the tensors.
Okay. Yeah. So it's just all I'm saying is we are interpreting the notion of tensor as wiring in parallel, and the notion of the additives, the with and the plus as wiring in series. So let me right. So grab this one.
I just don't understand why are we talking here about like running computation over two probes. So first so what we wanted to do is having a computation of T1 and T2 examining a frozen state, and why we see here in the end the computation of two probes.
Yes, so that's good. So remember, we don't get to write accessors like give me the first probe. The only thing we can do is we can form Ks, right? That's all that we're given. We don't have the luxury of saying, you know, let me use this. It'll be easier. We don't have the luxury of saying, you know, K T1 T2 dot first. All we can do is smash another particle that is a whole K against this one. And the way we do that smashing is by forming a K with it.
But first we were running computation of T1 against probe 1. So this would give us some output of probe 1, as I understood.
That's right. But remember, in order to make it whole, right? What we'd like to, so we are interested in accessing the T1 component and the T2 component. So we're going to so we can kind of open the box in the following way. We take this one and that one, and we run those two together with a K. And that will give us some information. And we take this one and that one, and we form a K with that, and we run those two together. And now, how do I accumulate the results? I don't have any way in this system of accumulating the results except by collecting these two results, putting them in a K, and if that runs, letting that run. That's it. That's all I've got.
Yeah, I got that.
Okay.
So first line makes sense.
And then the second one is go ahead and let this and this run together, and let the probes run together, and then run whatever you got coming out of this against whatever came out of that. So you can think about, one way to think about this is probing the inputs and this is probing the output. That's another way to think about it if it helps. Does that make sense?
Yeah, but we instead, so on the third line, instead of K, P1, P2, we can have just P3, for example. And this P3 is for examining the output of the joining execution of T1 and T2.
Yes, understood. But there's only one kind of thing you can form, which is a K.
Yeah, and there you have K of K T1 T2 with and then you have K. So you have outer K, and the second argument for this K will be just a probe. Why
Yeah,
to
but the point is that the only kind of probe that you can have is either a constant or a K. So you want to say that it can be some arbitrary program. So like the only thing that could be here is either a constant or a K.
Yeah,
So
probe.
so instead of, so what we do is, and since the constant will return is, there are cases where a constant might return some information. But the sort of the more interesting case is when this is a program itself. So you let your probe do its, think about this as the setup for the probe. Does that make sense? So this is like the initialization of your test.
I see.
Right. So this initializes the test, and then whatever is done after initialization is run against that. Okay. So parallel series.
Is it make sense or to reverse in outer K arguments? For example, in series.
Oh yeah, you can. Yeah, that you can do that. This is without loss of generality. So yes, there are you can run all those changes. Yeah, you can do P1 T1 P2 T2 T1 P1 P2 T2 etc. Right. So without loss of generality, you have we're just trying to show what the combinations are.
Okay.
Right. Yeah. But that's a good question. So hopefully that gives you some idea of what's going on, right? That there's we don't, in this game, we don't know anything about the computation, the details of how computation proceeds, because we've carefully abstracted that. We've said, I don't want to know. I just want to know enough about your model of computation that that allows me to get some insights into the structure and resourcing and collections and context, and that will be enough to say very interesting things about your programs. Like, it will allow me to type check and see whether or not your program's deadlock. It will allow me to type check and see whether or not you've got multi-threading in your program. It will allow me to type check and see whether or not you have a security leakage, right? All I need to know about your program in terms of the system is this much. And then all the other details, can be left to the specifics of the programming model. Does that make sense?
Yeah, I think
cool. So. And then the other two pieces. So this is the insight about resources, and then the other two pieces are that we're going to work over collections of programs, not just single programs. So this collection structure, up to here, this is really just finite sets. I know it looks like products, but it's really just finite sets, because we're going to have some rules that say whatever you can do with A paired with B, you can also do with B paired with A. So any tuple that is A B is also going to you can provide a uniform transformation across everything that will give you BA. So effectively, this is not ordered, it's unordered. And then the other thing that we're going to provide is a rule that says whatever you can do with A paired with A, you can do with just A. So if you have duplicates, they'll be removed. So that's what we know from logic, right? So A and A is the same as A, and A and B is the same as B and A, which means that even though we have tuples, they're really just finite sets. So it's a kind of low level representation of a set, right? It's like having a vector representation of a set. Does that make sense?
Mm-hmm.
So everything up to here is just the usual finite set formation. And then over here, this is map, right? So if I have a set and another set, I'm going to form the Ks of all the things from the first set with all the things from the second set. So it's just a big for comprehension in Scala, right? Give me all the pairs. Or you could think about it as a pointwise operation on K. Is that making sense? So if you gave me a set S1 and a set S2, then I'll form K of the first element from S1 with the first element from S2, and K of the first element from S1 with the second element from S2, and so on with all the first elements and the second elements and third elements and so forth, right? So this is all of them.
So all combinations.
All combinations. Exactly. So this is giving me essentially all the notion of collections, and then we extend it over all of these, right? So this is lifting these operations pointwise over finite sets. So if I know how to take an R of a program, then I could take an R of a set of programs by applying R over all the programs. If I know how to take an N of a program, I know how to take an N of a set of programs, and so on and so forth, right? So this thing is just lifting all of these constructors pointwise over the notion of finite sets. And then arrow is just going to be, all these are contexts. So it's a term with a hole in it. But we can make sets of contexts. That's why we start with sigma. You know, to be simple-minded, we would start with tau, but it's not really tau, it's sets of programs. So here, if you have a set of programs, then we know how to, if you have a set of programs with holes in them, then we know how to produce a set of programs with holes in them. So you know, the way to think about it is, you know, you just plug in the holes. So that's sorry, yeah. If you have a set of programs with holes in them, we can produce a set of programs. So whatever set you had as your arguments, you plug them in one at a time. That's one way to think about it. And the same is true, you know, you can close this up recursively. That's the way to say it. And then this arrow, the forward lollipop and the backward lollipop, the only thing that's going on there is that it's not just that you have a hole in your program. It's that you have a hole in your program, you've got some resource, and whenever you plug a value in from the left-hand side of the arrow, the lollipop, it always takes you to a value that's in the right-hand side of the lollipop. Right? So you plug the value in from the left-hand side. If there's any computational step at all, that computational step has to take you to a V that is in the right-hand side of the arrow. So you can think about it like these things are just your ordinary lambda. right? So I've got a program with a hole in it. I put a program inside that hole, and that's going to take me to a new program that has a particular shape, right? So the shape is basically described by this stuff here. And then this one says, I've got a program with a hole in it. I put a program in it, and then I take a step forward. I take a computational step forward, and then I get to a program with a particular shape that's described by what's up here. So this is about computational evolution. This is about filling in structure. Does that make sense?
Yes.
Okay. And with all of that, so all I needed was just this much specification about your programming language, and all of this comes for free.
Mm-hmm.
Right. So that's what makes this kind of cool.
Yeah.
Right. I'm only asking for a little tiny window into your programming language, and I can say a lot about your programming language, about how your programs evolve and how they're shaped. So,
and we don't need to expose these new constructors to this generated language, right? With this additional stuff that we know. So some of this stuff will be used by the type checker.
Yeah. So even though these appear to be terms, as long as your programming language is Turing complete, we know we can code these constructors here back into ordinary programs down here, so that we can trampoline. Yeah.
And some of them can only be used by type checker, for example.
That's correct.
Not
exactly.
successful.
Yeah,
Okay.
that's correct.
Okay.
Yep. We don't have to enrich the language. We can trampoline out of it. Yeah, that's exactly right.
Okay.
Good. See, asking questions, even though we have gone over that information many times, I imagine that it landed with you a little differently today because you asked some questions. I hope that that's the case.
Yeah, thank you.
For me also. Yeah.
Yeah,
I always find something to understand. Yeah.
Good.
When you were saying about the I'm not like in a position to understand how tiny is this K. So it looks cool, but then you're saying that then you need one tiny thing that's K, and to me it sounds like everything is K.
No, all we're saying is you in the case of lambda, K is just application. In the case of rho or pi, K is par.
Mm-hmm.
That's it, right? I mean, there's lots more structure to pi, but all I need to know is, par and the com rule, right? And 0 and whatever other constants you want to throw in. That's it. That's all I need to know. Or I need to know, application and abstraction, and that's it. That's all I need to know about your language.
Mm-hmm.
And the same, you'll have a similar kind of restriction for the Java, the Java virtual machine transition rules. Will have you'll get a similar kind of thing where you'll have potentially multiple of these rows here. These represent your transition rules. So in the case of lambda and rho, these transition rules are simple and essentially singular. But in the case of the JVM, you'll have a bunch of these rewrites, right? Because you get different kinds of rewrites based upon what's in the registers. But we can model We can model the JVM as well. The JVM will fit inside this shape. So we can go ahead.
I'm thinking how we in Scala we have Monix, and Monix is somehow like naive version of because it has a scheduler, and he's deciding what term will be like reduced in which moment. It doesn't have like real resources, but it somehow looks like.
Yes. You could definitely apply this to Monix for sure. Yeah. And you could insist, for example, that this could give you some constraints on your scheduler, for example, your scheduler semantics. You could write types down and then check it against the scheduler. And if the scheduler didn't, match the types, then you could complain, the program could complain.
Oh, we need to do this because this is often a problem.
We need to do this for 30 years.
Because it's very difficult to understand, to control what Monix will execute. It's somehow Monix is doing something, but execute one step is problematic. And I mean, I was reading discussions about that. It's yeah.
Good. We're making progress. Okay. Well, we have a dev stand up, which we're late for. I'll see you guys over in that channel.
See you. Thank you.
Thanks. Thank you.